Okay, fatty acid and triglyceride synthesis. Now, this is not really going to be happening in the fasting state because the whole point is, hey, we've got too much energy. We need to store it for later. So if you're in the fasting state, you're not going to have too much energy. You're going to be wanting to use your stored energy, not making more of it. So it doesn't really happen in the fasting state, but we'll talk about it, and we'll talk about in the fasting state what will inhibit this from happening so that we can use the stored energy instead of making it. So let's start over here. We've got excess energy, I said. So we've got glycolysis happening, lots of glucose. So glycolysis, pyruvate into the TCA cycle. Oh, guess what? We've got a lot of energy signified by a lot of ATP being made. So that is going to inhibit isocitrate dehydrogenase. We're going to get a buildup of isocitrate and citrate. Now, we've got a lot of citrate in the mitochondria. It's going to leave against its concentration gradient. It can become oxaloacetate. It can become acetyl-CoA, malonyl-CoA. We'll talk about that in a second. Citrate can also become malate, as it can down here, but this is happening in the cytosol, so malate. Now, malate by malic acid can become pyruvate again and keep this thing going, but in the process, malic enzyme creates NADPH, which is important for fatty acid synthesis, and then it's going to recycle the NADP and keep going. As this keeps going, we're going to use more NADPH over here. Now, we can also get NADPH from the pentose phosphate pathway. Remember, if we've got a lot of glucose, a lot of glycolysis, we're going to get some backup of glucose 6-phosphate. We're going to go into the pentose phosphate pathway, make us some more NADPH, and also we're going to get a backup of DHAP from glycolysis, which can be glycerol 3P, which then can be used for triglyceride synthesis later on. So we've got essentially NADPH coming in from excess glucose. So we're going to store it. So that is going to help build this fatty acid synthase. In the meantime, citrate has become malate. Over here, this is going. Citrate can also become acetyl-CoA. Remember, we've got a buildup of citrate, so it's going to go both directions, become acetyl-CoA, which will become malonyl-CoA. Now, malonyl-CoA is important because not only is it a building block in fatty acid synthesis, it also inhibits fatty acid oxidation, because you don't want to be oxidizing fatty acids at the same time as you're trying to build them. So malonyl-CoA will inhibit that process, as it also contributes to this process. So acetyl-CoA, malonyl-CoA, acetyl-CoA carboxylase inhibited by glucagon, but that's not what we're talking about at the moment. So these two are going to be used in a somewhat convoluted process by the fatty acid synthase to make fatty acids. We need biotin for that splicing to happen. Very important for that process. Now, fatty acids, palmitate, stearate, are made by the fatty acid synthase first. They are going to be transported by CoA and become triglycerides with the glycerol 3-phosphate from here. And then shipped out, or they will become phospholipids and used in the cell membrane and as second messengers. Now, down here, malonyl-CoA, we said inhibits fatty acid oxidation, also contributes to this process. Glucagon will inhibit acetyl-CoA carboxylase to prevent fatty acid synthesis, and encourage everything to work back this way into the TCA cycle. So in a fasting state, we've got no insulin, we've got glucagon. It's going to prevent this from happening by blocking this enzyme, no malonyl-CoA, so we are free to do fatty acid oxidation, and no malonyl-CoA will prevent this from happening, so all this will build up and go back into the TCA cycle because we've got, we're using up our glucose in the fasting state and no more is coming in, so we need this to happen and we need to stop it with the fatty acid synthesis. Real quick, I'll talk about, just to get back to what it is stimulated by, high energy in the TCA cycle, which inhibits this, causes a backup. Insulin activates acetyl-CoA carboxylase, opposite of glucagon. It activates this, so high glucose, high insulin means this is going to happen, means this is going to happen. We've already got a lot of this going on, so let's build some fatty acids. Now, high levels of G3P and or DHAP will also contribute to this process. Now, we need biotin, and we need a lot of NADPH to make this fatty acid synthesis happen. So those are important as well. Once again, the main way this is inhibited by glucagon because it blocks this and it says, let's get all this back into the mitochondria and make some energy that way. We don't need to store it right now. Okay, lipolysis, beta oxidation. This is what we're talking about in the fasting state. So we have all these triglycerides. We have these fatty acids that we've stored in times of excess energy. So now we're in the fasting state. We're going to break them down to be used as energy themselves. So what happens? Well, hormone-sensitive lipase is the enzyme that will snip the fatty acids. That will snip the fatty acids, and we'll get some long-chain fatty acids. We'll get some medium-chain fatty acids. The medium-chain fatty acids can go directly into the mitochondrial membrane, but the long-chain ones can't. So we're going to get fatty acid CoA. We're going to use a little energy, attach a CoA. Now the CoA is going to transfer to the carnitine acyltransferase 1. We're going to recycle that acetyl-CoA, and then the acylcarnitine is going to travel in the mitochondrial membrane to carnitine acylcarnitine translocase. And then it's going to actually come into the mitochondria. Remember, long-chain fatty acids can't enter the mitochondria directly. They have to take the carnitine shuttle to enter the mitochondria. And then once they're in, they become acetyl-CoA with a fatty acid. The acetyl-CoA is right here. This is our fatty acid. This is the beta carbon. Now we're going to snip 2 at a time. And in the process, we're going to be making some energy. What are we going to be making? FADH, riboflavin, going to be used in the electron transport chain. NADH, also going to be used in the electron transport chain. So we've got oxidation, hydration, oxidation, thiol. We've got a sulfhydryl and a CoA. That's all being used to break this down 2 at a time. Now, what stimulates lipolysis, beta oxidation? Hormone-sensitive lipase. So we're going to get glucagon is going to increase the levels of this or it's going to signal to this, hey, let's get to work. Let's start snipping our fatty acids. So we're in the fasting state. We've got no insulin. We've got glucagon. It's going to stimulate this to happen. We're going to get our fatty acids and we're going to get them into the mitochondria. Also epinephrine and cortisol. So that's not necessarily in the fasting state. That could be in a fight or flight situation. But that's also going to stimulate this to happen. Now, FAD2H, NADH, what we're making here, if that is being used and it doesn't build up, that's going to help this process continue along as well. So as long as these are going into the electron transport chain, we can keep doing this. But if they build up, that's going to cause this process to stop. So we need B12 for odd number fatty acid chains, which are not the rule but the exception. We also need FAD for this to happen, this oxidation, and we need NAD for this oxidation to happen. We also need some carnitine. That's important for fat burning because you have to get your long chain fatty acids into your mitochondria. Carnitine, the carnitine shuttle is how you do that. Now, in the fasting state, we want this to happen. We want to use our stored fatty acids to make energy. Now, what's going to inhibit that? Malonyl-CoA from fatty acid synthesis, which we just talked about. That's going to inhibit this enzyme so that the carnitine acyltransferase won't accept anything to be transferred into the mitochondria. So that is the way. Remember, malonyl-CoA is also used as a building block for fatty acids. So if we are doing that, we don't want to be breaking fatty acids down at the same time. So malonyl-CoA is going to be used in fatty acid synthesis, but also to block beta oxidation. Now, FAD2H and NADH right here, if they are not being used up in the electron transport chain, that will cause a backup, and they will also kind of stop this process from happening as efficiently. So that's what's going to inhibit it, and this is something in the fasting state that we want to be happening. Okay, ketogenesis and ketone oxidation. So the building of ketones and also the oxidation of ketones. That's what we want in the fasting state. And we also want to eventually be using our ketones for energy. So this is what we want to happen in the fasting state. So we have fatty acid beta oxidation, which we just talked about. Then we get some acetyl-CoA. Remember, the acetyl-CoA was recycled by the carnitine acyltransferase 1. So that's going to be recycled, and it's going to be used also to build these ketones. So eventually, HMG-CoA right here, we're going to get acetoacetate, which if that builds up, will also give us acetone, which is not a good thing. We want this process to keep going smoothly. So acetoacetate can also become 3-hydroxybutyrate. Now, those are our 3 ketones. So we're breaking down our fatty acids, we're getting some acetyl-CoA, we're getting energy from the fatty acid breakdown, but we're also building these ketones in the process. Now, to get energy from the ketones, we want to also break those down. So we have beta-hydroxybutyrate dehydrogenase, requires some NAD, we're going to get some NADH out of it. Now it's basically going to break these down back into acetyl-CoA, which can then be used in the TCA cycle. Now, the TCA cycle, if it's in operation, is also going to provide us some succinyl-CoA as part of this step, to continue the process to make acetyl-CoA to keep this thing going. That's where we get our energy from the ketones. So we've got building the ketones here with the acetyl-CoA, and then we don't want too much of these because we don't want to have too much acetone because that is expelled through the lungs and not pleasant. We want this to start to be broken down and get some more acetyl-CoA into the TCA cycle. So ketogenesis is stimulated by, so we're building ketones, and that is stimulated by low insulin. We don't have a lot of glucose. We're using our stored fatty acids. Low malonyl-CoA, remember that blocks fatty acid synthesis. It also activates the carnitine shuttle. So when you have low levels of that, we're going to have more beta oxidation happening, and therefore we're going to be able to get more of this. So high NADH used in ETC, the electron transport chain, for the same reason. That means we're getting lots of this happening. Fatty acid oxidation. Also, acetyl-CoA in the liver, buildup of acetyl-CoA means it's not being used elsewhere. We can make some ketones with it. Also, the HMG-CoA synthase, this enzyme right here, this enzyme is what makes the ketogenesis possible and therefore the ketone oxidation possible. So we increase the transcription of that enzyme, we're going to get more of this happening. Now, this process is inhibited by insulin. If you're in ketosis, you're making ketones and using them, and then you eat a cheesesteak or whatever, your insulin's going to go up. This process is going to stop. You're going to get malonyl-CoA, more fatty acid synthesis, and not the fatty acid breakdown that you want. So in the fasting state, when you're not getting insulin, this is what we want to have happen. And eventually, we're going to use those ketones. If you're in the fasting state long enough, you will start to use those ketones to make energy in addition to the fatty acids. Okay, cholesterol synthesis. Not really happening in the fasting state, but I will explain it, and I'll explain what inhibits it. Cholesterol synthesis, again, we've got all this energy. What are we going to do with it? Well, let's take some acetyl-CoA and let's get to HMG-CoA like we did in ketogenesis. We're going to get to the HMG-CoA. Now, we can either build ketones, but in a state of high energy, we're going to go this direction. And HMG-CoA reductase is going to give us mevalonate, and then we're going to go through the rest of the steps. Basically, isopentenyl pyrophosphate, geranyl pyrophosphate, farnesyl pyrophosphate with an isopentenyl pyrophosphate, and we're going to build our cholesterol. Now, key step in this process, HMG-CoA reductase. Now, If you've got AMP, low energy, if you've got glucagon, if you've got cortisol or statins, we'll talk about those in a second, these things are going to inhibit HMG-CoA reductase, and we'll probably use this then instead for ketogenesis, not for cholesterol synthesis. So low energy, high glucagon, cortisol is going to make that happen. Also statins. Now statins will inhibit this. They're a class of drug for cholesterol lowering that just basically block the rest of this from happening, which I don't know why that is any good for anybody, but whatever. Okay, so this enzyme also requires 2-NADPH. Now that was a result of some previous things that we've seen. For this to happen and for all this, for us to build our cholesterol. Cholesterol is important. It is the building block of a lot of different hormones, our steroid hormones. It's also used for structural purposes in our cell membranes. Now, cholesterol synthesis stimulated by high energy. We've got a lot of energy. What are we going to do with it? Let's make some cholesterol. And it's also stimulated by high reducing agents, which is the 2-NADPH, is going to help this process along. It's going to move everything in this direction from our malic enzyme and pentose phosphate pathway that we've already seen. Vitamin D. We also need vitamin D right here to actually build the cholesterol in this last step here. There are some other steps in here that I didn't get into. It's really more complicated than this, but this is the general outline. And this right here is the important part. So if we're in the fasting state, we don't want this to happen. We don't want to be building cholesterol. We want to be using up the energy for other things. So we're going to block this. AMP, low energy, is going to block this, going to send the HMG into ketogenesis. Glucagon, also going to do the same thing. Also stress, again, not necessarily in the fasting state, but stress for fight or flight, for quick energy that we might need. And we talked about statins. So that is the key enzymatic step in this process.
Okay, one quick last little pathway here. We have protein metabolism. We can see in the left corner protein digestion. Now, once those amino acids are broken down and absorbed, they can go into the amino acid pool. They can be transaminated, deaminated, in which case we're going to get some amino groups, some nitrogen, and which is ammonia. So the ammonia is going to go into the urea cycle. It starts in the mitochondria, carbomoyl phosphate, together with some ornithine, makes some citrulline. Citrulline with aspartate leaves the mitochondria, becomes arginosuccinate, which becomes arginine, which becomes ornithine again. But in the process, we make some urea to be expelled, and we've gotten rid of the harmful ammonia. Now, when arginosuccinate becomes arginine, we also get some fumarate, which is a step of the TCA cycle. So we're helping along that energy production. We can also get intermediates from the TCA cycle from transamination, which requires B6 to happen. And all of this together is constantly being interchanged with the amino acid pool, proteins and amino acids being used in all different ways, being replenished, being degraded based on their needs. Now, this whole thing is stimulated by protein digestion, but also ATP availability and the needs of the body at that moment for certain proteins based on transcription and what needs to be happening that way. And this process is inhibited mostly by low ATP availability, because even in the fasting state, you're going to want to be making proteins, but obviously if you don't have enough energy, that's going to be something that takes a back seat. So that is protein metabolism at a 50,000 foot glance.